Something very cool is happening right now, and we knew it was coming, and it's going to impact mechatronics and robotics, and especially the open source side of all this. And that is, as tools are becoming electrified, they're also becoming modular. So a really good example right now is in the outdoor power tools. We have weed whackers, is a really nice example, or trimmers that have been released as electric versions by all the leading companies by now. Echo is a famous long-standing company that makes power tools such as chainsaws and weed whackers. And right here, they've got one of their newest lines of tools. It is a modular tool where you change out what's on the shaft. So the part that they're selling as a complete product to start with is nothing but a battery, a motor, and a rotating output. And lastly, a control system that's measuring the battery and the motor and taking the user input to control that speed. It's one actuator. And I'm sure in some cases the battery is sold separately. So what that means is that when they break apart their product into two, this opens up a million new doors. One of the doors is in their business operation, they're going to gain the chance to outsource. Are we going to have these batteries manufactured by us, or are we going to start having this vertical de-integration, where the best manufacturers in the world use the best standards and release the best value for the power that's going into my tool? And then Echo will use its expertise in mechanical systems to make a brushless design that has the motor integrated and have hopefully a long lasting life. Then what's the end effector? What's spinning after it plugs into this rotating shaft? Could be a blade, could be the trimming line, or it could be wheels. It could be basically, this is not far off from a Segway. A Segway is two motors, a battery, and a controller that you can stand on. And what we have in the industry is that if you look at popular robotics companies like Boston Dynamics, they're putting an immense amount of engineering into one place, and it results in one product that looks one way, and it's one monolithic design. Half of the engineering was going into making these modules, the motors and the controllers and the communications, and the other half was going into integration. Well, how do we make sure that the power system supports all the outputs, and how do we make sure that all the outputs are fixtured rigidly to the machine? And in open source engineering, we have this this sharing that's going to happen, that's already happening, where we borrow assets from other entities, individuals or businesses, and you can have an open source invention that doesn't have to have completely open source development behind it. So they make an excellent competitive battery. We can purchase that, and now an entire power system has been solved for us. What does it mean for the mechanical space? Well, traditionally we're seeing projects and research projects, student projects, and business MVPs, minimal viable product, that has been built from the ground up. The quality is very limited on any first iteration of some robot because it's all been on the shoulders of one team. Now, if you have a robot with chainsaws for arms, suddenly you can purchase from a company that has invested heavily in the chainsaw design. Now, your job as a robot maker is to decide how will they move, how will it be powered, the motion of the chainsaw arm, but you don't have to design all of those links inside of it and how it's going to transmit power from rotation to a sliding chain. And you don't need to manufacture all of the components that are going to go into that. Now we can start to have building blocks instead of having this unbearable task of trying to create. Basically every robotics team up until now is usually kind of reinventing the wheel. I like to think about robotics the same as the path of personal computers. So a computer, as we know now, is a million different things, but the PC, the desktop in a box, is a nice milestone where consumer adoption became popular and it became affordable. And there was a range of possibilities. You don't need to have the NASA grade equipment. I like to compare Boston Dynamics Spot or the walking robot with the image I have from, it was the 70s, I think, late 70s, where NASA had a computer, and this is what a computer meant. It was an entire room full of equipment, all connected together and engineered in-house, that made computing happen. And maybe monitors are a whole nother story. But the only way to get from this extremely expensive machine that would also be really silly to have, even if you could afford it, it would be silly to have in your home. And the consumer space, that we don't know how to use a computer anyway. Microsoft Excel hadn't been invented. These simple tools that are useful for everyone in the world hadn't been invented. That pathway from the NASA machine to the desktop machine is just like this. But instead of it all being about the computer, now it's all about mechanical, electrical, and software, the combination of these. Now, so if you're imagining, in the future, people all across the world will have these in their homes, that robot is not the thing you see in the movie iRobot or the Boston Dynamics products. It's nothing like it. Just like the NASA computer is nothing like a personal desktop computer. The utilities are different anyway, so you wouldn't know how to use it. So what does that path look like? It is a very key ingredient to the path was the modularity of things. So the CD-ROM, invented, I don't know, by Sony or someone, was this standalone technology that was invented by one company, where in the 80s and 90s, most of us had a PC that had a CD drive, but that wasn't invented by the manufacturer of the computer. And if it had to be invented by the manufacturer, and all the other components, the power supply, the monitors, the speakers, these have to get segmented off. And then they're put together using standards. The standards start to come into play. If it's possible, they borrow something from a very long-standing past standard in another industry. But the standards are the glue that allow different companies with different expertise to produce the products that, okay, these can be compatible. And then that allows companies like Dell to say, all right, we're going to pick and place components from several manufacturers. Dell doesn't invent their own processors or design their own CD-ROMs. They are the integrators. And you can see, using Dell and HP as examples, that there's an immense value and immense effort just to make a thing come together, even if all the parts already exist. In robotics, we're seeing research teams treat their own tasking as, we're going to do the integration, and we're going to invent all the stuff. When students are 3D printing mechanisms, instead of just printing the joining fixtures that put two inventions together, they're sometimes printing whole assemblies for linear actuators that have been very refined for 100 years. Currently, it's my opinion that the world does not know how to do open source for mechanical technology. We're really good at open source software. That is, someone who's brilliant in an area creates a boxed in product or a function, a utility that is fully defined inside of a script that's digitally held and digitally reproducible, like 100% identical copy without degradation. When you look at open source software currently, we're treating it as well, in the bulk of the available open source hardware is student level or maybe small business level quality. It's not top tier. It appears to the business folks looking in to the engineering space that this is not mature technology. It is not high precision or highly competitive, and it's not something that you can build a business on. We know from software that's not true. So what are the barriers for hardware to become successfully open sourced and exchanged for profitable and sustainable businesses to use it, implement it, and participate in a way that enhances the community, enhances the space where all these designs exist? That barrier is standards. So if you invent your own software language and you write your code in your own language, it could be mathematically viable, but it's not something other people can use. And over time, the languages are standardized and popularized to where we start to converge on this is a good language to use for these things. Compilers to bring the software from the script onto a hardware machine for particular types of hardware. These categories of processors, the categories of machine languages became established, and the industry converged on a few different architectures. Now, those standards have to be created in hardware as well. What I'm seeing is that we're beginning to have the definition of a piece of hardware as a module to be established. So when Echo, a very large company, releases a module, and you don't need to re-architect the entire thing in order to use it. If you're an open source designer and you want to extract the utility of it, now, how is it characterized? The characterization is simplified into a few key parameters. How many volts and amp hours is the battery? How many, now that's on the energy space, so we could even say that's not mechanical. Then you have on the mechanical, what is the physical interface? What's the standard that attaches this shaft to this receiving, rotating assembly? What are the torque constraints, so that if you have two shafts together, how far can you hold it out, or how fast can you whip it around without it bending? So what is the expected, how can the user or the recipient designer take a module and understand, without re-engineering everything, the utility, the constraints, and the method that it takes to mate with it. This has been happening for batteries for some time, and now we're seeing it happen for full mechanical assemblies. And in the case of, let's say, CAD modeling, a lot of people think that an open source hardware means you have an open source CAD model. They're sharing the digital design of the innards, every parameter of the dimensions of the gears inside and every screw, the materials of the plastic. That's nice. That may be useful for adapting the design, but it's not necessary for the person to make use of the component. And so we simplify those characteristics, and then an electrical engineer can simply understand, oh, this is a motor that's going to drive between 0 and 800 RPMs, and it's going to have a few mechanical characteristics that an engineer can understand when they're not in the exact same discipline, when they were not on that design team, and when they don't have access to the full CAD model, the full assembly, everything inside of it. We're boxing things in. The next step is for robotics companies to adopt some of these mechanical assemblies that are sold on the market at competitive consumer pricing, instead of performing an entire engineering collaboration to make something come out. Now, the robotics company simply purchases, and maybe they start purchasing in bulk, the mechanical modules that are released by a company in a totally different space. And company A, who invented the module, they're not complaining. They're happy. Their sales numbers go up because the blades on a chainsaw can do a lot more things than cut down trees in the backyard of the consumer near a Lowe's store. Houston Mechatronics is an example. It just popped in my head. They make underwater robots. Maybe there's a utility where most of the components of a chainsaw can be brought underwater to perform a task in deep sea where they're remote operated. Houston Mechatronics, it's a submarine. It's a UAV, unmanned underwater vehicle. Anyway, they could probably benefit with some special application you haven't thought of. And as many tools start becoming modular, and we can pick parts off of the shelf instead of redesigning everything from scratch, it's going to be a beautiful new thing. And then you have a new space, just like the personal computer, where you need a power supply. You want to add a joystick instead of a mouse. A joystick isn't commonly found on all the computers, but some people want to do flight simulators. And then you, as a techie consumer, can understand, okay, this joystick would be useful for my PC game, and they purchase it. It formerly was, perhaps the joystick manufacturers were companies in the arcade space. They made products that belong in the arcade at the mall, and then they pivoted to start making these modular joysticks. And instead of Pac-Man, now the whole entire new market space can use it for flight simulation. And as this happens, then mechatronics engineers can start to understand who they are. They really don't know who they are. And when you visit mechatronics education programs, 4-year degree that's for engineering, but what is inside of mechatronics currently? It's mechanical engineering, it's electrical engineering, electronics engineering, computer engineering, and software engineering. Well, how do you get 5 degrees in the time it takes to get 1 degree? You can't. And so these folks are all the way up to the program makers. I'm talking about students, TAs, professors, and the professors among them who are leading the creation of these programs. They're not sure what needs to be included in a mechatronics degree. It's a new territory because there are too many facets for it to have meaning. If you tried to spread it out evenly, your degree program would have you a jack of all trades and a master of none. Well, I think that there is a solution to be found, but the solution still depends. This definition of a mechatronics engineer is it's centered on integration. How do we graduate engineers that can integrate items that are produced from the mechanical space and the software space, etc.? How does the sensor work in the level of detail that tells you how to use it, but not necessarily how to invent it? This solution does exist. There is a way to learn mechatronics in a 4-year degree. It will not make you as proficient as a mechanical engineer is in mechanical engineering. And currently, when you visit colleges in their senior design projects across all the US, and I'm seeing so many worldwide, the projects of these students, the students are being tasked with inventing something. And you will see the electrical engineers stumbling their way through CAD programs to make mechanical things that are haphazard. They're doing their best, and mechanical engineers that are stumbling their way through software to have a microcontroller collect data and log it. We're having computer engineers that are buying very expensive parts because they weren't exactly sure how to sort through mechanical and electrical options. And this is why robotics feels expensive and burdensome and overwhelming in the number of things you need to know. And this is going to get simpler. So the simpler, it's very related, the simplifying is related to the transition from an engineer to a technician. I'm going to have a technician level understanding of thermodynamics. Well, which parts of thermodynamics, since you can get a whole PhD in that? Oh, it's the part where energy gets balanced, energy storage is understood, quantifying electrical energy in an electrical system. I'll be capable enough in that to know how to choose a battery. And that's it. And then we'll know from industry and from our education modules that are taught in colleges, we'll know, okay, what are the key values that have to be compute when I'm choosing a battery that are not only they're rooted in thermodynamics, but they're also matching the way that engineering components are sold. Are they sold, categorized, listed? And when you go to McMaster-Carr to purchase some mechanical brackets, you will be able to also go to the online suppliers for modular systems, such as this Echo machine. It's not just a motor anymore that specifies torque. It's a motor with a gearbox and a simple controller. It's going to be self-regulating in the speed and the torque or something like this, and those figures will be taught. How do we understand those figures so we can pull them back into our engineering computations that we learned? Then your mechatronics engineer has the technician level understanding of all these disciplines, and that technician level understanding is matched to the current industry. And maybe give it another 10 years, but this means that folks that have an existing skill set, let's say you are an expert in just one engineering discipline. I see every engineer I bump into is self-training on some other discipline. Oh, well, I'm trying to learn software so I can control this better. And that self-training can, instead of a billion different options, what are you going to choose? And how quickly will that get outdated? That will be easier to choose. And when we can train ourselves better, we can have more direction, and outcomes can be more amazing. Then you have more willingness to participate in open source collaborative designs worldwide, because it makes so much more sense to do it. Okay, I know this discussion has been all over the place, and it's one of the reasons why it's hard for me to segment a concept into one piece and then publish a video or some dialogue or an article to explain a concept, because they all have to come together at once. There's not a standalone concept that is I found I can break off into a piece. So it's all just like the economy drives technology into new places and cost reduction. It all happens together. So I'm very well aware this may have been a little bit hard to track, but let's try to tie this together. We're electrifying a lot of appliances and mobilizing them, so they're not plugged into a house anymore. We are then making the inventions modular, which gives way to collaborations and exchanges between businesses and inventors and designers. That collaboration gives way to standards, where the fastest way to exchange these assets is by simplifying how we will do the big picture, so that the small picture says just where do you plug it in. And those standards give way to open source. The activity we do in open source can capture things that are not claiming open source, or they're not developed open source, or some very big company has paid for a lot of engineering. Then that exchange has been, I've related it to the computer space, where we saw software can do amazing things now, and it couldn't do it in the 70s. And it's not because we got smarter, it's because we're stacking. We're standing on the shoulders of giants. We are borrowing modules on top of an operating system. We have a software application on top of a software application. We have a script, and on top of the script, we have a developer that creates something useful, like an app on your phone that can bring loads of value, and that only costs that individual or the company a small effort, small number of years, so we can return big, massive rewards that previously would have been $1-million projects with sometimes in a weekend. And then we said, between the analogy of how software was made open source, allowing us to make these exchanges and add value much more rapidly. In the hardware space, the standards that we form will make way for simplifying. Simple characteristics can be denoted in a design, when suddenly all you need to know is the shaft length or the RPMs or some few basic characteristics. And then the open source community can capture this invention and utilize it. And that company, that closed source company, still gets paid. And we realized that open sourcing had nothing to do with what was your business model. It was how engineers, designers, and creators can make exchanges much more rapidly, digitally, using the internet. And the only way to take a physical object and make it digital, and have that digital object have meaning, is if you can fully characterize it. We know it's hard to characterize a physical object with bits and bytes. It's a lot easier with software, and it's going to get easier, because with the trust that this company complied with the standard, all we need to know is the radius, the length, and the width, and now we know the shape of this. Now we can mechanically fit it in, and suddenly open sourcing of mechanical and full-blown mechatronics systems it's just happening, and we don't have to push for it, but we certainly should define it. We should define what are the needs that get met when an asset becomes digital, and we can share it, so that other players can join in and collaborate, meeting the same needs and seeing the benefits much more clearly, instead of grinding at this push to try to convince folks to open source stuff. And instead of asking designers to double down on their efforts and say, well, if you don't publish this and document this, then it's not open. We can take this open sourcing piecewise and gain benefits, even if the entire project was not intended to be open. It's just happening.